Today we have two learning targets. First, we're going to simplify radicals using the multiplication and division properties of square roots. And secondly, we're going to simplify fractions with radicals in the denominator by rationalizing the denominator. So before we get too far, we should probably talk about what exactly a radical expression is. Well, a radical expression is an expression that contains a radical. But what exactly is a radical? Well, a radical is an expression that uses a root. It can be a square root, a cubic root, a fourth, fifth, sixth root, an infinite root, whatever you choose. It is an expression that uses a root. And these are the elements of a radical or radical expression. It has the degree of the radical, so we have a cubic here. We have the radical symbol, and then we have our radicand, or what is underneath the radical symbol. The expression underneath the radical symbol is the radicand. Now, what we are interested in doing is simplifying the radical. A radical expression is simplified when, and this is very important, these are the three things that have to be done. The radicand can have no perfect square factors, right? So you can have the square root of 4 in there, square root of 16, square root of 25. A radicand can contain no fractions, so there can be no fractions underneath the radical symbol. You can't have that. And there must be no radicals in the denominator. So if you've got your bottom part of your fraction, there can be no radicals down there. So here are some examples, and I'll move me so that you can see. These are simplified. You notice here there's no perfect square factors. 5 has no perfect squares, contains no fractions there, and it has no radicals in the denominator. Same here. And of course, even though this is a fraction, it contains no fractions underneath the radical symbol, and there are no radicals in the denominator. In this case, however, we do have a situation where there is a perfect square. 4 times 3 gives you 12, so you could take the square root of 4, and that would give you 2. This has a fraction underneath the radical symbol, and this one has a radical in the denominator. Let's go ahead and get down to the business of simplifying some roots. One of the tools that we have is the multiplication property of square roots, and how that works is this. We can take a square root, and we can break it down into the factors that make up that square root. So for example, 48 it has 2 factors, 16 and 3, so we can split those up. And the convenient thing here is that 16, its square root is 4, so we can go ahead and take the square root of 16 and then simply multiply that by 3. We had a perfect square in 16, we took its square root, got 4, and then we multiplied that by 3, which has no perfect squares. And we can apply that down here to some of our problems. The square root of 160, for example. If you punch the square root of 160 into your calculator, you're going to quickly realize that it's not a perfect square. However, we can break this down into the factors of 160. So we could say that the square root of 160 it has 2 factors, 16 and 10. So we could say it's the square root of 16 times the square root of 10. Now that's convenient because, again, 16, we know that it's a perfect square. So we can say that that is 4. And then we can simply write that as 4 times the square root of 10. What about the case of the square root of 52 times x? Well, we can see that 52, if we think about it, what are its factors? We know that 2 of its factors are 4 and 13. 4 and 13. So we can write the square root of 52x as the square root of 4 times the square root of 13 times the square root of x, if you want. Think of it like that. Now, we know the square root of 4 is 2. We know that square root of 13 has no more perfect squares. It's a prime number, so we'll write the square root of 13. And since we have x all alone out here by himself, the square root of x is going to be kind of weird too, so we'll just write that as x. Now, if it was x squared, if the square root of x squared was underneath there, what would that be? Well, that would be x. So we could then take that out, and we're going to look at that next. But for right now, your answer is 2 times the square root of 13x, all using the multiplication property of square roots. Now you'll look at these problems and notice that they have variables in them, much like our last one did that we worked on. If you remember, we had a variable underneath there and we had to do something with it. So this gives us a little bit more opportunity to practice that. In this case, though, we don't have a single n, we have n to the 7th. We want the square root of 54 times n to the 7th. Now hopefully, as you look at this, you can see that 54 has a couple of factors that might be useful to us. For example, 54 divided by 9 is 6. So I could write this as the square root of 9 times the square root of 6. But what do we do with the variable, with the n to the 7th? You'll recall last time I pointed out that the square root of any number that has been squared is equal to itself. So the square root of n squared is actually just n. Just like if we had the square root of 2 squared, well, this 2 squared is 4. So that's equal to the square root of 4, which is equal to 2. So in this case, the square root of n squared is equal to n. But we don't just have n squared, we have n to the 7th. We will recognize that n to the 7th is actually the same as n squared times n squared times n squared times n. So we have n to the 2nd plus the 2nd plus the 2nd plus 1 gives us a total of n to the 7th. Now each one of these n squareds is equal to, when we take its square root, right? If we want to take the square root of n to the 7th, we take the square root of n squared, and that gives us just n. And the square root of n squared is equal to just n, and the square root of n squared is equal to just n. And the square root of n is equal to, well, the square root of n. And we are left with n to the 3rd times the square root of n. The way to look at it is that the square root of n to the 7th is really just equal to the square root of n to the 6th times the square root of n, and then take the square root of n to the 6th, which is going to be n to the 3rd times the square root of n. So let's go ahead and apply that over here. That's going to leave us with the square root of n to the 6th times the square root of n. Now we can simplify this. The square root of 9 is a perfect square, so it's going to be 3 times the square root of 6, which is not a perfect square. And let's go ahead and simplify this one too, because n to the 6th is a perfect square. It's n to the 3rd. And then we'll have times the square root of 6n. We'll combine these two terms right here to get the square root of 6n. So now we've combined all our terms, 3n to the 3rd times the square root of 6n. One last problem here. In this case, we've got a variable out front, and we've got some things to simplify on the inside. So we're going to write this as negative m. We know that's going to stay the same. What are the factors of 80 that we could use here? Well, we know that 4 goes into 80. But 16 also goes into 80. It goes 5 times. So I'm going to write this as negative m times the square root of 16 times the square root of 5. And then I'm going to deal with my variable, right? Because I know that I've got to split this up so that I can have an even power of this m. If I take that m to the 8th, and that'll give me m to the 8th there times the square root of just m. Now remember that any variable raised to an even power is going to have a perfect square. It's going to be a perfect square, so it's going to be to the power of whatever it is now divided by 2. Just remember that as we do this. So negative m. Now, this square root of 16 is actually 4, so I can say that's times 4. Times the square root of 5, which it doesn't have a perfect square. M to the 8th is a perfect square of m to the 4th, and then times the square root of m. And then we can just rearrange these guys a little bit. What you need to do is think about this much as you would combining like terms. So for example, I see that I've got 2 squared values, and we'll treat those just like we would our variables, if you will. So we'll keep those separate, and then we'll combine, first of all, we'll combine all of these. So if we multiply negative m times m to the 4th, and we have an implicit power of 1 there, that's going to give us negative m to the 5th. Times 4 is going to give us negative 4m to the 5th. And then all we have to do is take care using our product property, our multiplication property of roots, and we get the square root of 5m. So that brings us to simplifying radical expressions using multiplication. So in this case, you'll notice we have 2 radical expressions being multiplied by each other. How can we simplify that to make it a little bit easier to read, to make it clearer? So what we can do to simplify these is we can take these variables using the distributive property, right? We can multiply the 2 times the 3. That's going to give us 6. And then we can simply multiply these by themselves as well. So that's going to give us 6 times the square root of 7t times 14t squared. Simply multiply those numbers, and 7 times 14 gives us 98. It's 98. And we multiply the t's together, so t to the first times t to the second is t to the third. But we're not done. We need to make sure that we continue to simplify anything that's under the radical. So our radicand is 98t to the third. If we look at 98 and think about it, what are some perfect squares that could go into it? We find out that 49 times 2 actually gives us 98. So we can write this as 6 times the square root of 49 times the square root of 2, that gives us the square root of 98, times the square root of t to the second, right? Because we want to make sure that we have this to an even power because we can take the root of that, and then times the square root of t. So we wind up with 6 times the square root of 49 is 7 times the square root of 2 times the square root of t squared, which is just t, times the square root of t. And then we combine just as if they were like terms. 6 times 7 is 42, and times t gives us 42t, times the square root of 2, t. And we're done. This video is getting way longer than normal, so what we'll have to do is break it into two, but let's do one more problem. So we will simplify using multiplication here. 7 times 3 is going to give me 21, and then 5 times 20 is 100. X to the first times x to the fifth is x to the sixth. So we wind up then, if we want to split this up, we can say this is 21 times, and the square root of 100 is 10, we know that, and the square root of x to the sixth. So let's go ahead and work that out. 21 times 10 times and the square root of x to the sixth. Remember, we simply divide its power by 2, x to the third. So we get 210 x to the third. And we're done.